We now take a look at generic routing encapsulation, or GRE, for support of protocol encapsulation where encapsulation is not naturally supported. Limitations within IPsec VPN restrict the ability for routes to be carried between disparate site-to-site based networks, and allowing only for static route solutions. GRE provides a mechanism for the encapsulation of packets of one protocol into packets of another protocol. The application of GRE is as such implemented as a primary solution to the IPsec VPN limitations, for which knowledge of GRE is necessary to complement the existing knowledge of IPsec VPN. So upon completion of this section, it is generally expected that trainees will be able to explain how GRE can be applied to provide various solutions, describe the principal behavior of GRE, as well as configure GRE over IPsec. The implementation of IPsec VPN solutions to securely support the bridge between remote office networks over the public network domain allows a greater interaction between remote networks that effectively belong to the same administrative domain. One of the key issues, however, is that IPsec VPN is unable to support the carrying of dynamic routes, which means that in terms of establishing remote enterprise networks, such networks must currently rely on static routes in order to direct traffic and build connections. In order to overcome this issue, however, it is possible to employ generic routing encapsulation, or GRE as it's commonly known. GRE itself was originally used to support transportation of non-IP protocols over IP, however provides a valid solution for supporting the tunneling of dynamic routes together with IPsec VPN. The implementation of GRE is also able to overcome issues that affect other protocols, such as in the case of RIP. The Routing Information Protocol, as we are aware, supports a hop limit of 15 hops, which effectively limits the scale that the Interior Gateway Protocol is able to support. Through the implementation of GRE, however, it is possible to build tunnels over which these routes can be carried, that allows for the overall scale of the network to be increased beyond the common limitations. GRE itself, however, provides only the capability to encapsulate one protocol within another. It, however, provides no means for establishing secure connections for this protocol traffic as it is carried over the network. Due to this, we may often find GRE coupled with IPsec VPN solutions in order to provide a best of both worlds outcome that enables tunnels to be created, that encapsulates protocol contents within GRE, and for IPsec VPN technology to be used in order to securely transport the GRE payload over what is often a public network, such as the Internet. We see here the typical process that is involved and how GRE is implemented to support the transportation of the payload. Typically, we will find that a packet is generated by an end station and forwarded to a gateway device or interface that represents the edge of a GRE tunnel. The physical interface is usually bound to a tunnel interface that is employed by GRE to support the transport of the GRE encapsulated payload. We show here a payload of data and the GRE header that is used to encapsulate this payload. The original IP header is also encapsulated and replaced by an outer IP header in the same manner as seen with the IPsec tunnel mode. This new IP header supports the transport of the GRE payload between the endpoints of the GRE tunnel. The source IP address of the new IP header is therefore the IP address of the local tunnel interface, and the destination IP address, the remote address of the tunnel interface. The link layer may represent varying link layer protocols, such as Ethernet and Frame Relay. Within the GRE header is the means to support authentication on the tunnel interface. In implementing authentication through GRE, it is possible to prevent the tunnel from identifying and receiving packets from other devices. We show here the typical format of the GRE header and highlight the fields that relate to the key authentication. The bit field represented by a K here will be set with a value of 1 if key authentication has been enabled. The key itself is carried in a key field and represents a 4-byte value that is used for authentication that is performed by both the sender and receiver. The key is related to a traffic flow, and so packets from the same traffic flow will use the same key value in the key field. Authentication of packets is considered successful if both ends of the GRE tunnel support the same key value. Another feature of GRE is the ability to detect the state of the connection through keep alive messages. It is necessary to ensure that both tunnel interfaces are active and that the tunnel itself maintains connectivity over which GRE traffic can be forwarded. Generally, we would find that without the use of keep alive messages, GRE would provide no mechanism to determine the state of the connection to the remote end or the peer tunnel interface. Packets sent in such circumstances would experience loss of data without notification. The keep alive function, however, is optional, and where enabled will generate keep alive messages every 5 seconds. We should also note that the keep alive function need only be configured on one of the peering tunnel interfaces, since a generated keep alive message will be responded to by the peer. In order to implement GRE, we are required to firstly establish tunnel interfaces that are in fact logical interfaces that are assigned with an IP address, an address that will function as the external IP address for the GRE payload over the GRE tunnel. We see here that the IP address for the local tunnel interface is configured as 40.1.1.1/24. GRE is then set as the protocol to be supported over the tunnel interface. A source point and destination point for the tunnel is then configured, which in this case is specified using the address for interface gigabit Ethernet 0/0/1 on RTA as the source point, and the equivalent address of interface gigabit Ethernet 0/0/1 on RTB as the destination. If dynamic routing protocols are advertised, they will be carried over the tunnel and shown within the peering device as being received via the tunnel interface. In this case, however, we have created a static route to inform RTA that local packets destined for network 10.1.2.0 should be carried over the tunnel interface. Once the tunnel interface has been configured in order to support GRE, we can use the display interface tunnel command to view the respective tunnel and validate the commands configured. We should generally find that the tunnel interface is showing to be in an up state and that the line protocol is up, which indicates that the supported link layer protocol is active over the tunnel. The internet address here is set as 40.1.1.1/24 for the tunnel itself, and that tunnel is configured between interface gigabit Ethernet 0/0/1 of both RTA and RTB, based on the tunnel source and destination addresses shown. We will also notice that the MTU is set here to 1476. This is because GRE will generate an additional 24 bytes of overhead as a result of the additional headers and payload. We are therefore expected to reduce the MTU size using the MTU command in the tunnel interface view to reduce this to 1476. In doing so, we are able to compensate for any additional load and optimize traffic flow by avoiding unnecessary GRE packet fragmentation. We can use the display IP routing table command to determine the forwarding of traffic over the tunnel interface. We can see here that traffic destined for the 10.1.2.0/24 network will be forwarded over the tunnel interface with a next hop of 40.1.1.2, which is the tunnel address configured on RTB. If dynamic routing is configured, we will observe specific routes for remote destinations in the routing table as they are advertised over the tunnel interface. Keep alive messages are configured within the tunnel interface view using the keep alive command. In addition to this, we are also able to set the keep alive period that is to be used, as well as the number of times that a keep alive will retry in the event that a response is not received from the peering interface. Here we have changed the period to 3 seconds. However, for the number of retries, it has not been configured, meaning that the default number of retries will be used. If we again return to the display interface tunnel command output, we will now find that the keep alive function is enabled on the interface and that the period has been set to 3, whilst the number of retries remains as the default of 3 retries. We will also notice that configuration of the keep alive feature in this instance has only been configured on RTA. As such, we are able to validate the status of the tunnel connection, since keep alive status responses will be returned by RTB without requiring that the keep alive feature be enabled on the peer. So to summarize this section on GRE, we just have a couple of questions here. The first asks, what is the primary application for using GRE? Well, primarily, GRE is used to support the transport of protocol traffic over other protocols, such as, for example, Novell Network IPX protocol data over IP networks. It is now, however, adopted to support the transport of dynamic routing protocol traffic over a site-to-site created tunnel, and as such, is often used together with IPsec VPN technology. This allows a secure private tunnel over the public network to be formed, to establish dynamic routing between disparate enterprise networks. What is the difference between the internet address and the tunnel source in the display interface tunnel command? Well, we can understand the internet address to be the virtual tunnel network address on which GRE is established, whereas the tunnel source defines the point at which the tunnel is established and the destination as where it terminates.